Good morning. It is 10 a.m, so it is time for our Physics with Keith live tutorial. I'm trying something a little bit different today. I'm streaming directly from OBS without having gone to the website first, so I can't actually see how many people are online watching this. But you know, never mind, it's no great loss. What I wanted to remind you is that this is an interactive live tutorial, which means that you are able to go onto YouTube and comment, and your comments will then be read by me and I can respond to them. So I'll show you what I mean by that. If you go to let's get the right page, there we go. So if you go to YouTube, you can see there's me, there's my video there with a slight delay, and now we're going into fractal land. But there's my video there with the delay, and here on the right hand side of where the video is, you can see there's a chat box where you can type something, hello world, and then everyone gets the message. So you can talk to me through chat like that, and I can see that live as that happens, or you can also send me messages on my phone through Facebook Messenger if you prefer, and I'll get those messages and I can respond to them as I go along as well. So let's get rid of that. This is the last session before the summer holidays, but don't worry, because we're going to do a summer holiday physics revision thing. We're going to be doing, let's move this to the side so I can see if anyone chats. Yes, we're going to be doing physics revision all summer long with a summer school, which I'm quite excited about because I now have had so far 9 people subscribe to it, and everyone's welcome to join it. The likelihood is that there'll be topics you have covered already if you're in year 10, topics you have covered and some topics you haven't, or maybe you're in year 11 and you're thinking that you might want to take the exam again in I can't remember when it is now, but in the autumn term you might want to take the GCSE exam again because you might not be happy with the grade that was awarded. Well, in that case you can go do this summer school and be in a slightly stronger position when it comes to that. Or alternatively, maybe you're in year 9 and you're preparing for your GCSEs and you're thinking, well, this might be a good way to get ready for it, or maybe any other year, year 7, year 8, and you think this might be a good way to prepare for your GCSEs. That's a really good idea, but just do bear in mind that there's not going to be a series of long videos that you watch. This is going to be a summer school where you answer questions, and if there are topics you don't understand, that's fine, and you can ask me about that, and I've put instructional videos up there and things like that, and I've got more videos I can share with you. But the purpose of the summer school is to get you doing stuff, to get you thinking, to get you working through problems. And there will be problems you see that you can do and problems you see that you can't do, whether you're in year 7 or if you're in year 11. That's going to be the way it is, and that's okay. There's no reason to feel disillusioned or disappointed or put off. I can't think of the word I'm looking for. But never mind. You don't want to feel like that if there are questions you can't do. It's designed that way, especially because I'm trying to cover as much of the course as I can. I can't spend, like you would in school, 3 weeks on one particular topic. Instead, there'll be one question on that topic. And if you find you can't do it, or you don't understand it, or you don't remember it, don't think, well, that's it, I can't do the rest of these questions, because the next question will be on a different topic, and so on and so on. And if you find one week you can't do any of those questions, that's great. We've discovered something. We've learnt that there's an area of physics where you need to develop. Ask me about it, or if you're doing it through Isaac Physics, I'll see your progress and I'll know that you're struggling with that. And so I'll be able to then talk about that using the live tutorial like this. So that's sort of a brief introduction, but that starts today. I'll be uploading the instructional videos and the first assignment today for that. But today really was a last chance to do this live tutorial about any topic you want. Now I haven't had any questions come through yet, and I can see that there are, it says 2 people watching now, but one of those will be me. I'll just press refresh and see if that changes. I wish I hadn't pressed refresh. Now it stopped working to see if that changes. But at the moment, It doesn't look like very many people are online watching this, so maybe you're thinking you'll have a week off. That's a shame. So if you do have any questions about any topics at all while this is live, put me on the spot. It's fine. I can help you with that. And what I thought I would do today, in the absence of any anything coming through from people, is I would have a look at some of the key equations that you're going to need for this first week of the summer school. Just ease you in a little bit in case there's anything you're not quite sure of. Because the instructional videos I'm recording are very, very short, very, very quick, and don't really go into the physics very much as they do help you with those questions. So the first thing is, let's just list the equations that are relevant to the topic that we're talking about. And so the very first equation, the first topic we're doing is the mechanics topic. I think, I will double check that, but I think it's the mechanics topic. So the first, let's open this book up and check. Yeah, mechanics topic. So the first equation that you're going to need is speed equals distance over time. Now in physics we always use a V or a U for speed. We don't use an S, never use an S for speed. S in physics means displacement, not speed. You might think that's weird. Maybe it is weird. I can't give you an explanation as to why, so please don't ask me for one. But it's just the way it is. Speed equals distance over time is a little bit of a vague equation. We use distance, we use an S. Again, please don't ask me why. That's just the way it always has been and the way it always will be. I'm looking at this thing here and it's not showing up on my screen, which is making me a little bit nervous on the live stream. But I wonder if that's because my live stream is delayed. Ah, yes, it's delayed. Might not do it this way in the future. Okay, so what we mean with this equation is actually the average speed, and I'll turn my pen round. This here is an average speed, and this over here is a total distance. So we're having to be a little bit more specific, because of course you'll have met that equation in Key Stage 3. You'll have met that perhaps in Year 7, one of the first equations you ever meet. But in physics, we also have other equations. For example, we have an instantaneous speed and we have an average speed. And so they're not quite the same thing. But if your speed is constant and doesn't change, then a speed at an instant in time is the same as an average speed. Okay. In some notations, vectors are indicated with arrows over the top. That's certainly the notation that's preferred, was preferred when I was at the University of Manchester. However, when I was at the University of Salford, they preferred to underline vectors, and I believe they also preferred to underline vectors at Cambridge. In printed text, you'll find vectors are bold. So what on earth is a vector? Well, I'll ask you, is there anyone out there on internet land? If you're out there, then please comment. Tell me what you think a vector is. At the moment, it looks like there's one person watching. No messages have come through on the Facebook Messenger. It looks like there's one person watching live on YouTube. So what do you think a vector is? Drop your comment there now, please. I'll wait 7 Mississippis and then I will carry on. If you're new to this and you've never seen this before, the reason why I'm counting 7 Mississippis is because there's a 7-second delay between me saying something and you hearing it. So that's the latency. So I tend to count 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi, and that gives me enough time to know that you've heard the message. Okay, so no one's commenting. So if you are watching, you're not playing along live, you're not asking questions or answering, that's fine. If that's up to you. So I'll just give the answers then. So if we have a vector, that means it contains information about the direction of the quantity as well as the magnitude of the quantity. So this quantity here, S, because it's bold, it's a vector, isn't distance anymore. That is displacement. And this quantity here, V, because it's bold, isn't speed anymore because it's now a vector. It is velocity. So just be careful of whether we have direction or not. And some quantities have direction and some don't. For example, speed doesn't, distance doesn't, velocity and displacement do. Acceleration is a vector, but deceleration is a scalar. There's interesting things like that. Energy doesn't have direction. Momentum does. And so on. So that's the very first equation, a nice easy equation. And you can think of that as the definition of velocity, the rate of change of displacement. So a difference in displacement divided by time. And if we draw a graph of displacement, and I'll use the arrow notation for a vector, divided by time, then the velocity is the gradient of this line. So let's just draw this on like this, and let's have some numbers. Let's say that this is displacement measured in meters. So this is 10 meters, this is 20 meters, this is 30 meters. I'm writing the unit next to each number, which is bad practice, but I'm doing it anyway. 40 meters, 50 meters, and so on. So let's say each square represents 10 meters. And let's say each of these squares represents 2 seconds. So 2 seconds, 4 seconds, 6 seconds, 8 seconds, 10 seconds, 12 seconds, 14 seconds, 16 seconds, and so on. So when we look at this graph, we can see that we go from this point on the graph. As time marches on, we end up over here in this point on the graph at some time later, and so on and so on. So because we are travelling a certain distance, in fact we're being displaced a certain displacement in a certain amount of time, we are moving, and we are moving with a speed. Super. So Ted can now answer questions. I've just seen a little message come through. That's great news. Thank you very much for putting a little note on here. I was worried that I was all by myself then for a minute. Yes, we're rolling now. We have people out there in internet land who are able to interact. Now I feel better. You can tell that 'cause I've got a big smile on my face. So how far have we travelled between these 2 points on the graph? Well, we started 40 meters away from the origin. We finished 60 meters away from the origin. So I'll open it up to you, internet land. How far have we travelled? How far have we been displaced from that origin, from zero? One Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi, 7 Mississippi. Can I repeat the question, please? Yes, I can. I absolutely can repeat the question. So this graph represents motion, and in this graph, which is representing motion, we've got 2 points. The first point here is 4 seconds after we started moving, and the next point here is 12 seconds after we started moving. What I'm interested in, how far have we travelled between those 2 points, between 4 seconds and 12 seconds? What's the displacement, which is a distance that we've travelled in a particular direction? And let's assume we're travelling in the same direction to keep this simple. So reading off the y-axis, we started 40 meters away from some origin, some point where I'm measuring distances from, or displacements from. So we started 40 meters away, and then we finished 60 meters away. So how far have we travelled? So it's the quantity I'd like you to give me is represented by this arrow here. "20 meters. That sounds absolutely right to me. So this on the graph is 20 meters. Now we have the time axis. And on this graph, between those 2 points, so the stopwatch started running, then that first point, the stopwatch showed 4 seconds, and that last point, the stopwatch showed 12 seconds. So what is the duration between those points, the time? How long has passed between those 2 points. Eight seconds, yes, perfect, correct. You see, physics is easy, isn't it? I don't know why people fuss about it, he says jokingly. So 8 seconds. So now if I want to know the speed that we've travelled, or technically a velocity, because this is displacement on the y-axis. Because if I want to know how fast we have travelled, then how fast we've travelled is s, which remember is not speed, it's either displacement or distance, divided by t. That's the definition of speed and velocity. So on this graph we've got 20 meters and we're dividing that by 8 seconds. So how fast have we gone? And you're welcome to use a calculator. You will never ever ever in a physics lesson ever be told you can't use a calculator. I often get students asking me, sir, are we allowed to use calculators in this exam? Of course you can. The reason why you're allowed to use calculators is because I can't do maths without them. So if I can't, you can't be expected to either. How fast have we travelled? 2.5, and you've got a unit there as well. Absolutely perfect. 2.5 meters per second, because we've gone 20 meters divided by 8 seconds. So the units divide as well. My writing has gone under my face. Look at that. Let me move that around a bit. There we go. That should be fine. So, 2.5 meters per second. That's also the gradient of this line. And that's the next point you're supposed to realise, and the reason why I've drawn it this way. Now, if you don't know what gradient of a line is yet, that's fine. Can't be expected to know if you've never been taught it. But the gradient of a line is the slope of a line. The steeper the gradient, the steeper the slope. Or should I say the larger the gradient, the steeper the slope. And sometimes students remember how to calculate gradient as rise over run, which means how much we have gone up on the graph divided by how much we've gone along on the graph. And you can see that that's exactly the calculation you've just done. How much you've gone up on the graph is 20 meters. How much you've gone along on the graph is 8 seconds. The speed was 2.5 meters per second. So rise over run. Now, when you learn gradient for the first time, your teacher may very well start talking about triangles, and they'll say, oh, you need a very large triangle to get an accurate gradient and things like this. And you'll think, what the devil are they talking about? Triangles. But if I move those arrows, those arrows that I added to the diagram so we could see clearly what I was measuring, you can see that that is clearly a triangle, and that's what we're talking about. Now, when you first learn gradient in mathematics lessons, possibly in year 7, or it depends what your school curriculum is, then you may very well learn to count squares. And so if you count squares, you'll go, okay, this is 2 squares, this is 4 squares, and 2 squares divided by 4 squares is 0.5. So that's the gradient. And that's the sort of thing that is done in mathematics. Be very careful in physics to look at what's happening on the axes, because on the axes we can see that counting the squares here is pointless. A square here is 10 meters, a square across here is 2 seconds, so we can't just count squares and then divide numbers of squares. It doesn't make sense to do that, so just be a little bit cautious of that. So that's the first equation, speed, and then I've taken that equation, that definition of speed. We talked a bit about velocity and speed and what the distinction between those two, and we looked at a graph representing motion, and we related the idea of speed as the gradient of a distance time graph, or velocity as the gradient of a displacement time graph. So now let's have a look at another equation. Let's just get rid of this graph for a second. You know what, I can just scroll down. Let's have a look at another graph. Another equation, sorry, and this is another key definition, and this is acceleration. Now, acceleration is defined as the rate of change of velocity. So a change in velocity, would represent that with a triangle, the Greek letter delta. That means a change. So a change in velocity divided by, now on some formula sheets it just has a t here, but the mathematician within me finds out, I'll leave it like that, that's the way it appears on formula sheets. So change in velocity divided by time. Now, in most places in physics, a lowercase v means final velocity. Can mean average velocity, or it can mean final velocity. Remember, velocity is a speed in a particular direction. And we use the letter u to indicate initial velocity. So, what do you think delta v will equal? A change in velocity. Write it in the chat now. You don't need to write the delta v part, but what do you think it equals? 1 second, I'm going to have to mute my microphone because I just heard a bang from upstairs and that makes me nervous. My daughter just dropped her drum and I heard a loud bang. Yes, V minus U. Just do be careful to use lowercase letters. Capital V tends to refer to volume in physics, and the capital U tends to refer to internal energy, I think. I'll have to look that one up. So try to avoid using capital letters in mechanics. These are lowercase letters. But yes, absolutely. V minus U is the change in velocity. So this equation is often written as V minus U divided by t. Okay, now let's have a look at a graph. Let's look at some motion. So here's a graph, and this time we're going to have a graph of velocity. That's how fast we're going. And just imagine we're going in the same direction to keep it pretty straightforward. So velocity versus time. And let's have time measured in seconds. Let's do it properly and put the units on the axes this time. Velocity in meters per second. And let's have 10. Let's do the same intervals as last time. 30, 40, and so on. And let's have the same intervals as last time. Let's keep it nice and simple. 6, 8, 10, and 12. And let's say that our motion looks a little bit like this. Now, the first mistake students make is if they see a graph like that, they think there's no motion because the line is horizontal. But the graph is showing velocity, and the velocity is 20 meters per second. So there clearly is motion. Things are moving at 20 meters per second. So that's a very common mistake that's made. Now, what is happening in the motion here? So in this motion here, the thing that's moving is getting faster. And you can see that it gets faster by a certain interval. It gets a certain amount faster in a certain amount of time. So I'm going to ask you the same question I asked you last time, but let's see if you can do it all in one step by yourself. I'd like to know what the difference in velocity is. I'd like to know what the time interval is over which that difference in velocity occurred. And then I'd like to know what the acceleration is. And let's see if you can give me a unit for acceleration as well. So 3 questions in one. Did I unmute my microphone? Yes, I did. So, step by step, working it out. If you don't know the unit, just say you don't know the unit. There's nothing wrong with that. But have a guess. See if you can get it. Try. Okay, so you've put S equals 20. There's two issues with what you've written. T does equal 14, and there's an issue with what you've written there. So where you wrote S equals 20, you've missed the unit off. And also it's not S. On the y-axis now, it's not S anymore. It's V, or delta V. So the number part was right. This is indeed 20, but it's not 20 meters. It's 20 meters per second. And the time across here is, as you say correctly, 14 seconds. So make sure you include the unit. Okay, so now what I want to know is what the acceleration is. Okay, so I've given you a little bit of time. The answer hasn't appeared on the screen just yet. I wonder if that's because you're wrangling with the unit as such. So maybe just write the number down, and we'll see if you've got the numerical part right to start with. So I'll give you 7 Mississippis. Oh no, you've got the answer there. So 1.429, which is correct to 4 significant figures. I haven't checked it to more significant figures. Let's have a look. Yeah, that's correct to 4 significant figures. Meters per second, and then you've put the 2 there, and I think, yeah, you're right, but let's write it slightly differently. So 1.429 to 4 significant figures, meters per second. So we've got 2 per seconds. So we could write it like this, but that would be a bit odd, and people don't really write things like this. But remember that if a number appears after a division, then it's on the denominator of a fraction. So it's on the bottom of a fraction. And so we've got this seconds on the bottom of a fraction and this seconds on the bottom of a fraction. So that's 2 lots of seconds on the bottom of a fraction, which usually we would write as seconds squared on the bottom of the fraction. And I think that's what you meant when you wrote meters / seconds and then the 2. Another common way of writing it in or typing it is to put meters per second and then maybe put the, I think it's called a caret, and then 2. That's another common way of indicating you mean to the power of. Or if you've got a keyboard on your computer with a numpad, you can hold Alt and type 0178. I think that gives you a squared as well. I'll just test that now. Let's see if this works. So meters / seconds. Oh, that's some small font. Let's make that bigger first. If you're doing it on your phone, then this isn't going to work. So meters per second, Alt 0178, boom, there we go. And you get yourself a little squared symbol. Little shorthands that you learn sometimes. So, okay, good. Let's have a look at what we've learned from this then. We've learned that on a velocity time graph, the gradient is the acceleration. We've learned that we can find the acceleration if we have 2 velocities and an interval of time between them. All good so far. The thing about velocities is it can go up as well as down. Displacement can go up as well as down. Distance can only go up. So you can only increase your distance. You can never undo a distance you've walked. If you've got one of those pedometers that count the number of steps you've done, you can walk out of your front door, walk around, and go back to your front door, and the number of steps you've done has increased while you've been walking. You can't unwalk those steps and make the number on your pedometer go down. You probably reset your pedometer, but that's not the point. Whereas your displacement, because from a position, your distance to that position as a straight line has gone up, and then as you've returned to the starting point, it's gone back down again, your displacement can be 0, but your distance wouldn't be. So displacement on a graph can go up as well as down. Distance can only go up. Speed can go up or down, and so can velocity, but velocity can go negative. The good news is you don't have to deal with that at GCSE level. If you have a gradient of your line that is negative, which means that it's sloping downwards, the final value minus the initial value is negative, then you have a negative gradient, you have a negative acceleration. And in this case, that means that you start fast, you end slow. So you have slowed down. So if you have a positive velocity and a negative acceleration, you are slowing down. And so that is deceleration. How many L's do you reckon in deceleration? I reckon 2. No, that's not 2. That's just wrong. Let's go with 1. Deceleration. Whereas if you have a negative velocity and a negative deceleration, so your graph goes even further down, something like this, then you can see that we've decelerated in this part because we've been slowing down. Our speed is going from 10 meters per second down to 0. And then after this time here, whenever that is, our speed is increasing because it's now negative 10, negative 20, negative 30 meters per second and so on. So our speed is increasing. We're getting faster, but we're going backwards. And because we're going backwards, we wouldn't say that we're decelerating. We are accelerating now. We're accelerating with negative, that's 1L by the way, it's just I've curled it over. We're accelerating with negative acceleration, but we're not decelerating because we're getting faster. So just watch out for that as well. Right, so part of what you're going to be doing in the summer school is looking at equations like that. Acceleration, deceleration, and this is in the first week. Velocity, speeds, displacements, and so on. And reading graphs. And on graphs, remember that the gradient of a velocity time graph is acceleration. Gradient of a displacement time graph is velocity, and things like that. There's also going to be questions about momentum, questions about moments, questions about, I can't remember, let's have a look. Momentum, moments, I think terminal velocity, I put a question in there. Circular motion, I think I put in there as well. So there's an awful lot that you may never have met before if you haven't studied any mechanics yet. But that's okay. Read the hints on the Isaac Physics question. Read the hints. That's going to help you understand the topic. You can ask me questions and I can go through that the following week on a Saturday. Or if you ask me questions, I can even send you links to videos that I've recorded already. So I've recorded videos for all of the topics through my school, but I just can't put them publicly. But I can show you the link to them privately if you want to. I mean, I recorded them, so I think that means I own the intellectual property. So I can send you the links to those videos if you get stuck. But I don't want to do that for everyone straight away, because then all people do is sit there watching videos, and the idea of the summer school is that you're doing questions. If you find there's a particular topic that you struggle with, maybe it's motion graphs, you can ask me and I will send you a question generator, such as this one. This question generator is for motion graphs, and in this particular one it is producing, well, this one's showing speed time graphs. They don't have to be speed time graphs. So in this particular question, you would be asked, what is the acceleration in the first leg of the journey? What is the acceleration in the second leg of the journey? And then finally, what is the distance travelled in the first, second, and the total distance travelled? Now, how do you think you find distance travelled from a graph like this? Do you know? Might have mentioned it before. Just going to unpassword this so I can draw on it. Yellow highlighter pen. Oops. No answers coming through. Not sure how to find the distance travelled. Okay, so let's just think about units for a second. We have a speed measured in meters per second, and we have a time measured in seconds. I need to do something with those 2 units to end up with just meters. So what do you think I have to do? Can I add them? Does that work? Can I subtract them? Does that work? Can I divide them? Does that work? Yes, seconds cancel each other out if you multiply them. You said so seconds cancel each other out, but that only happens if you multiply. So if I multiply meters per second by seconds, I get just meters. So on a graph, what we're talking about there is multiplying whatever's on the y-axis by whatever's on the x-axis. So in mathematics, if I had a shape and I multiplied the x-axis distance by the y-axis distance, let's say a and b, and I multiplied a by b, what would I be calculating on a shape? Area. Perfect. We'd be calculating the area. And that's exactly what we do. So to compute the distance travelled on a graph like this, you would find the area. And I often joke with my students, partially joke with my students, that the only reason they learn how to calculate an area in primary school is so that they can use it in their A-level physics. And it's true. It's in many ways. The only reason why we and this is my opinion, and it's going to upset non-physicists, but this is my opinion. The only reason why you do anything is so that you can learn, so that you can do physics. So look, we can break this into 2 shapes if you prefer, a triangle at the top and a rectangle at the bottom, and you can find the area of the triangle, the area of the rectangle, and add them together. That's one way of finding the area. The other way of finding the area is to use the Trapezium Rule. So with the Trapezium Rule, what we do is we take the average between the top and the bottom, which is about here-ish, and so that's what, 5.5, and multiply that by 8. So 5.5, this is a thick pen, multiplied by 8, and that would be the area of this one. And of course, because it's meters per second multiplied by seconds, that's meters. What is 5.5 multiplied by 8? Let me just plug that into my calculator. Oh, it's giving me beeping noises. Okay, 5.5 multiplied by 8. This gives me 44. It's a shame I couldn't do that in my head. 44, and if I click on answers, it gives us a distance for that first leg of the journey, step 1, of 44 meters. So that's how this sheet works. You click on the answers tab at the bottom, and it tells you the answers. So if you want practice, if you find that in the Isaac Physics questions there's one and you think, oh, that's really beating me, that question is very, very difficult. Hey, that's great, you found something you can learn from. So now what you need to do is ask me for some more questions, and I can send this to you quite happily. There's another skill that comes up, which is the moments, and of course I've got a question generator for moments. I mean, as a general rule of thumb, if there's any topic that comes up in physics, I'll have made a question generator for it, or I'll be in the middle of making a question generator for it. There's one I'm currently working on. So on this one, for example, it asks you to find the missing length. That's why there's a question mark here. So when you're doing the summer school, if you find, oh, I can't do this topic, I've never met this topic before, this is all brand new, read the hints. Maybe ask me for an instructional video, because I've got plenty of them that I'm not sharing publicly, or then ask me for some more questions just to practice that skill a little bit, and then go back to the Isaac Physics question and see if you can do it. And you know, that's how we're going to learn. That's how school works. And finally, the good old-fashioned question generator. I've set this one up, which has just mechanics questions on it at the moment. And if you go through there, you can see there's data, and we have to calculate time taken, mass, acceleration, momentum, mass, and so on. So if you find that the mathematical questions are beating you, then ask for the question generator and get some practice in before you try them again. And that's the plan. Right, I've been talking for 40 minutes. Are there any questions? Please do ask. Now is the time to ask. No questions? My phone screen went off, so I've not been watching it. See if there's any questions on. No questions through Facebook Messenger. Okay, so we'll call it a day there. What I'll do now is I will set that Isaac Physics assignment. I've got it ready to go. I just have to hit one button. I will make the video for the first instructional video public, and I'll put a little post on Facebook that gives some. Let me make it so you can see my face properly, because you don't see the screen anymore. And I'll put a post on Facebook just outlining what it is that we need to do in this first week. I'm in school Monday to Wednesday, so I'm probably not going to be able to respond very well to any questions you have during that time. But I'll be checking about once a day to see if anyone wants me to send them any extra help. But I do want you to see it as a bit of independent work until Saturday, when we can go through things together. I'll call it a day there. I'm going to see if the Facebook thing, this is the first time I've ever tried it, where I'm controlling the stream from OBS directly rather than using the Facebook website to start and stop the stream. So we're going to see if this works. I'm going to stop the stream now. Thank you very much for coming. I hope you all stay safe. Hope you all enjoy the summer school. I'm looking forward to it. I even set up an Edmodo page, but I've decided not to use it because it's just another password to have to remember. We'll just do everything through Facebook. But I'm looking forward to it. I think it should be fun. If you're not doing the summer school, why not? But if you don't want to do the summer school, then start back with this Saturday in September when school starts again. This will be here, free tuition, for as long as I'm able to, just to support people as they need it. Do subscribe to my channel if you've not already subscribed. Tell your friends. Get the more people involved in this, the better. So far, as I say, we've got 9 people signed up for the summer school, which is fantastic. Yes, Ted said he enjoyed today. Good, I'm glad you did. And I know the school that you're going to in the future, Ted, you are going to love it there. I promise you. Right, I'm going to call it a day. Have a lovely weekend. Stay safe, and I will see you all next week.